Good evening. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Genoa-Milan High-Capacity Railway Line, Italy's largest engineering project. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Webuild. Webuild is a major global player in the large-scale infrastructure sector, with over 114 years of experience worldwide across 50 countries. Webuild has long-standing relations and partnerships in the US, the United Emirates and Saudi Arabia, and services Australia's needs by supporting its long-term vision as it develops its infrastructure across the country. With clients in 50 countries worldwide, Webuild aspires to find forward-looking and sustainable solutions that create growth and innovation, while connecting people and the natural environment under the most challenging environmental conditions. Today we will hear from subject matter speakers, followed by an insightful panel discussion and audience Q&A. And I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our moderator for today, Peter Wills. Peter is an experienced transport infrastructure professional who is working as a transport subject matter expert on the Melbourne Airport Rail project. Peter also is the chair of the Victorian branch of Engineers Australia's Transport Australia Society. Melbourne Airport Rail is a transformational public transport project connecting Melbourne Airport to Victoria's regional and metropolitan train network. Peter applies both his international and Australian experience to integrated transport infrastructure projects, diverse teams, and complex transport problems. Please welcome Peter Wills.
Thank you, Amanda, and welcome again to our viewers joining today's session. I'd now like to welcome our first speaker, Leonardo Degatti. Leonardo has earned a master's degree in civil engineering from University of Illinois in 2000, and has since then he has been actively working in tunnelling and geotechnical projects in Italy, Europe, and America. He's been involved in the design and construction of several tunnels, including the high-speed capacity rail line Bologna to Florence, the TBM tunnelling projects in Turkey, the Autostrada Pedemontana Lombarda highway system, and the SARC highway. Since 2014, he's been working in Terzo Valico job sites, and currently he's responsible for the design of underground works for Webuild in the Terzo Valico dei Giovi Genova Junction 1 project. Please welcome Leonardo Degatti.
Thanks a lot, Peter. Thanks for the introduction. Welcome. I'm happy to share the experience that we have in this challenging project, which is Terzo Valico dei Giovi, or simply Terzo Valico. So I will make a brief introduction and overview of the project, and then we will go on the field to see some implementation of what we have done in this project. Then Remo will speak about challenges and innovation in our project, mainly with the TBMs. And finally, Carmine Dauria will speak about safety in Terzo Valico. Here is an overview of the project. This is basically high capacity, high velocity railway line between the city of Genoa and Tortona, as you can see on the right. It's a pretty large project. Just to give you some numbers, we have contract value of more than 4 billion euro. We have 5,000 people employed in this project. The project is also part of a bigger project, which is the Trans-European Transport Network, the TNT network, as we will see later on. So let's focus a bit closely into the project. As I was saying before, Terzo Valico is a high-speed, high-capacity railway line. Is the one colored in red in the map on the right, on the bottom, and basically it's the last part, the last piece of a larger line, which goes all the way up from Italy to Switzerland, Germany, and finally Netherlands. This part of the railway line is 53 kilometers long, but it has been built mostly underground. You can count almost 90 kilometers of tunnels. Contract value 4.3 billion euro. As we will see, we are general contractor in terms of Webuild. And another important data is the design speed, which is, since it's also high velocity, is 250 kilometers per hour. That will mean that when the line is finished, one can reach Milan from Genoa in an hour. Today is an hour and a half. So it's quite a saving of time. This is the current route of goods that go from China and eastern countries to Northern Europe. So what's basically happening today is that the container ships, most of them, they prefer to go the long way, all the way up to Rotterdam through the Gibraltar Channel, instead of going to Genova. So they go all the way up, and then they go down again with the train to serve, to bring the goods to those countries. Which is basically quite strange, because it's a longer trip with 5 days of delay of travel time and a bigger cost. The reason of that is basically the actual situation of the transportation system of Genoa. This is the photo of Genoa from the sea. You can see the port. You can see the surrounding, the mountains that make this town quite isolated, and makes a very big limitation for areas to deposit all those containers. So what is still a pretty big port, because it's one of the top 10 biggest ports in Europe, but still has some limitations. This is why this project of Terzo Valico is quite important. Also, because today most of the containers are loaded into trucks, and they move through roads. And the idea is to transfer all of this into train. The line is part of a larger system, which is called the Rhine-Alpine corridor. Is one of the corridor of the TNT network, and completion of the line, of course, will have many benefits. Just in terms of environment, that means a huge save in travel time and in CO2 emissions. Compared to the maritime transport, minus 70%. And this line is one of the most important lines in Europe. You have to consider that basically you have almost 4,000 kilometers of railway lines that go across all those countries, which are in a very densely populated zone of Europe. So you have almost you have 180,000 people in this area, and is part the whole system, the whole corridor, which is the red one. You can see on the left with the circle where we are at, is one of the busiest in Europe. That's why it was considered among the priorities. The European Union defined 10 corridors as the so-called core network, and the purpose is the target is to complete them before 2030, and we are working in that. A bit more about the project. So the project, as I said before, consists in 53 kilometers of new railway from Genoa to Tortona, basically, with the possibility of switch in the northern side also in direction of Turin. Most of the line is underground, which is the southern part. The southern 37 kilometers are underground, and the northern part is in the flat lands of Piemonte. It runs mostly open air. There are two major tunnels, Serravalle tunnels, which was completed, 7 kilometers, and a bigger one is Valico tunnel, 27 kilometers. Is actually the longest tunnel that we are building in Italy, and because of that, the construction uses 4 edits that are, used for speed up the excavation, and also will be used later on for emergency purposes and maintenance. Also, you can see in this slide the geological profile is a sketch of the geological profile. In the middle part of the alignment, the cover, the overburden, is about 600 meters in difficult rock. This is the layout of the tunnel. Basically, there are 2 twin tunnels which are spaced around 30 meters apart, that run parallel, and they are connected every 500 meters with cross passages. Also, you can see the location of the edits here. A couple of words about Webuild, who we are. We are a global leader in large, complex infrastructures. We build basically in all around the world, 50 countries. We have a lot of experience with challenging projects. So now I will focus a bit more on how we have organized such a big work. It's a big work that has 5,000 people working all around the job sites. In order to deal with that, we decided to build our own facilities, our own base camps, which are located basically from Genoa all the way north, all along the alignment. They are like small cities. They can host from 300 to almost 500 people each. Each of those base camp is fully organized, is integrated with the surrounding territory, but it also has some degree of independency. Of course, there are the dorms, the offices, there is a canteen, and also very important, there is an infirmary So in case of emergency, we can deal with that. And Carmine will explain this better later on. Very quickly, we have already done 77% of the work, so we are going towards the end. I said before, the Serravalle tunnel is completed today. We're excavating the Valico tunnel, which is the longest one. This tunnel here is excavated in two methods. You consider that 55 kilometers of the tunnel in Terzo Valico are excavated with the conventional excavation, whereas 35 are excavated with the TBM excavation. Of course, one can ask why is that? I will explain it in a few seconds. Before I show where are located all the job sites, there are 12 job sites along the alignment, and basically there is a big distinction, big difference in terms of characteristics of those job sites. If you go all the way down to Genoa, you will see that those job sites are mostly in a urban context. They are smaller. They are located in a very densely populated area. And then, if you go in the central part of the project, you have totally different types of tunnels. So you have mountain job sites. They are very, very small. It's pretty difficult to access to the places in this part of the project. The existing network is very, very small and limited. And when we go north in Piemonte, it's another context again, large flat areas, very, very easy to have access to the roads, and there is much more availability of sites for managing the muck coming from tunnels. So this contest around the alignment, around the new line, played a major role in deciding and shaping what was the type of job site and the type of excavation that we could perform. In each area, we had to choose different techniques. This is a photo in close to Genoa. This is Polcevera site. This is a site that was equipped for conventional excavation. As you can see, the site is pretty well integrated in the surrounding. You almost don't see it, but it's on the of course on the right. But it's pretty small, considering the importance of the works and the number of kilometers of tunnel to be excavated. In this situation, normally we used also other areas, to facilitate, to help with the management of muck, mainly, also for other needs. This is another scenario. This is Castagnola site in the bigger photo. So very small job site. Again, these are not very suitable for TBM excavation. There is no much space for muck management. We usually used conventional excavation in those sites. Usually they are equipped with a small concrete plant to make them, independent. And also it's interesting on how small and how how small is in terms of impact on the environment. In some situation, like in the little photo on the top left, we used a pre-existing quarry area that was already there, so we built our job site inside. And also, we used a dedicated belt system to bring our muck and to close the same quarry. So at the end, the result was quite sustainable. And this is a typical example of job site in the northern part. So the bigger photo is Radimero site, which is operating now. The smallest one is Serravalle site, which is completed. Both of them they have more space for segment stockage and muck management, and basically they are they are perfect for a TBM excavation. So, if we want to answer to the question before, the choice of technology, the proper technology to use for the different job site is basically a sum of different factors. You have to consider, of course, the technical aspects, the geology, which was mostly feasible. I mean, it was possible to excavate in TBM for sure in the north part, and it was more complicated in the central stretch of the project. And the type of tunnels, they play also a role, because in the southern part it's not only two tunnels, but there are a lot of connections, so it's more complicated to deal with the TBMs. But also you have to consider the logical constraints around. So basically they are the ones that I said before, the highways and in general the roads around the job site in the central part in the mountains were very, very complicated and to implement a TBM tunnel. And also the areas that were available for muck management were very small in most of the alignment, and we had instead a huge availability in the north part. So basically, at the end of it, we decided to use conventional excavation in the southern part and TBM excavation in the northern part. Thanks a lot. I leave the word to Remo. You will speak about challenges and innovation.
Grazie, Leonardo, for your input. I'd now like to welcome our second speaker, Remo Grandori. Since 1984, Remo has been working in the field of mechanised tunnelling, starting as a TBM site engineer and ending up as a technical director for some of the most important tunnel projects executed worldwide. Furthermore, since 1987, he has participated in the development of several innovations in tunnel and TBM's design, acting as a consultant to clients, contractors, and TBM manufacturers. His cooperation with the Webuild Group is back to the late 80s, and it continued until today, having been involved in the study and execution of several major TBM projects in North and South America, China, Europe, Africa, and lately in Australia. Please welcome Remo Grandori.
So we are going to speak about the challenge in TBM excavation, the innovation that we undertake in a large railway project in Italy, in the Kochiv project. I will speak about the main challenge in the project, how we manage these challenges, and how we implemented the innovation and what are the results and the lesson learned from this process. We employed 4 9.8 meter diameter APB TBMs to excavate very long tunnels under the Apennines, that is a mountain chain in Italy with very, very complex geology. We have here a view of the geology. What is really interesting that these are sedimentary rock with conglomerate, shale, argillitic rock, and with very large overburden, so 450 meters of overburden. This is very important because it's the first time that APB TBM that are normally used in urban context with, say, limited cover have been used with with extremely high overburden. In hydrogeology, quite also complex because we had, of course, under such a high mountain, high pressure of water and high flow of water, and also the presence of methane gas and asbestos minerals. So really, this project combine most of the difficulties and challenge that you can have while boring a tunnel by TBM. So this is a geological section of the tunnel showing basically the probability of crossing amianto asbestos formation, sorry. And as you can see, there is a section that of 400 meters where the probability of asbestos formation was very medium high, but actually very high. So we were sure to cross asbestos formation, and that's why we prepared, let's say, the machine, the TBM, in advance to manage this asbestos formation. So we didn't consider this as a risk, but as a matter of fact, we will have asbestos in this section. Then how we, well, in general, the TBM, and especially an APB TBM, gives some advantage when dealing with asbestos formation, because an APB TBM actually has a closed mode of operation, so the muck, at least inside the TBM shield, is confined in the excavation chamber and in the screw, so it is relatively easy to create separate volume inside, let's say, the machine and inside the tunnel. And that philosophy to create separate space was used to develop the idea and the design of the system. Basically, we considered a contaminated area that goes from the TBM up to the nearby the portal, not exactly the portal, but in proximity of the portal of the tunnel. So we have to say that this was considered a contaminated area, but we did our best in order this area not to be really contaminated, and we will see after. So here we can see a small video on how we organize the site. You can see here the outside installation. You can see the pool, the muck pool, where we deposited the muck and we tested the muck for the presence of asbestos. and this is the site from where the two machines that were crossing the asbestos formation were launched. This is the tunnel in the, let's say, so-called contaminated area. Of course, okay, these are just detail of the installation of the segment. These are detail of the covering of the conveyor system outside, not to disperse fiber outside. So all the external conveyor were covered. Then this is in proximity of the portal, let's say, to separate the contaminated area from the outside area that has to be non-contaminated. We had a decontaminated section. We can see now in the area A, in the contaminated area, the personnel was wearing full protective clothes and mask, so it was fully protected. Although we, as we can see afterward, we measure, we succeed in avoiding the presence of fiber by confining the Muck. But anyhow, since this was considered a contaminated area, we wanted people to be protected anyhow. You see that the belt, all the Muck transport system were contained inside the TBM and backup, and along the tunnel, the Muck that was kept humid by spray, and the return belt by wash box. Anyhow, at the end of the contaminated area, there was an area B, the contamination area, where the people, the air, and the vehicles were decontaminated. You can see some of the operation of the contamination, and these are the filters that were filtering, so decontaminating the area coming out of the tunnel from asbestos fibers. Here is the section where we wash the vehicles going out, the multi-service vehicle going out from the tunnel. And I think this is quite interesting to see this detail of the measure we took to clean the cabin. And then this door, they open, and then the vehicle could run out of the tunnel, where there is the area C, that is the non-contaminated area, that is all out the outside, let's say, space. This is, of course, very important, because what is inside the tunnel, you have to protect the worker from contamination. From what is outside the tunnel, you have to protect the environment from contamination. So these were the two targets we had, and I think we succeed well. Okay, still detail of the conveyor system. Say that the material outside was tested, and if asbestos, okay, now I think it's good to mention the monitoring system. We had monitoring system continuously testing the presence of fiber in all the three areas. No? And this was on 24-hour base. We have several fibers tested with SEM, that is the more accurate. We made 14,000 tests that gave us really confidence that we were doing the right work. We were working properly. So this was done in cooperation, also in agreement with the union and with all the authorities for the take care of quality, safety, and health in public authorities in Italy. Okay, that's I think very interesting, this video. Now we come to the result. No, we had 14 stations to measure the presence of fibers inside the TBM in the B area, in the decontamination area, and in the outside area, in the non-contaminated area. 14,000 measurements been done. We can see some of these stations. Then the results were this. So this is, I think, is quite important to see. So the limit given by the norm in Italy is that in the decontaminated area we cannot exceed 2 fiber per liter, while in the working area we contaminated, where the people wear protection clothes, we can go up to 100 fiber per liter. Our results show that these were taken in all the area, that in all the area we, for 98.8% of the time, we were below, and most of the time much below the 2 fiber per liter. So we basically, for 98.8%, even the contaminated, theoretically contaminated area were actually non-contaminated. Only in a very limited case in the area A, in the contaminated area, and we measured slightly more fiber than what is allowed in decontaminated area. So in short, by the measure we took, we managed to keep for 98.8% everywhere a decontaminated condition. Only in very few instances, we went up to the norm, but in the contaminated area where the people anyhow are protected by the protecting clothes and mask. So I think this explains the success of the operation. The Muck, that another is the last, let's say, problem, what to do with the contaminated Muck. In Italy, the norm legislation are quite strict. So let's say the normal Muck was loaded on truck after being tested, and again, for the management of the TBM material, we have two separate, say, corridors. One for the non-contaminated Muck, which non-contaminated by asbestos, but that contain foams for the condition of the PB. The Muck was from the Muck pool loaded on truck. We built a road, and say a dedicated road to transport with the truck the Muck that contain foaming material conditioning agent, to a very large intermediate deposit, the Romanellotta deposit, where the Muck was stored in stockpile, each pile for 1 day of production and only 1 meter high. So this in order to facilitate let's say the biodegradation of the material. And this was quite successful, because after an average of 7 days, 10 days, depending the season, we measured that the Muck was, say, decontaminated from the foam and could be transported to the final Muck disposal area. You can see this was quite an expensive operation, but quite successful. On the other side, it's not in the video, the contaminated Muck by asbestos was contained in special bag, in big bag, and transported inside the big bag to a special deposit that are in the northern part of Italy.
Thank you, Remo, for your input. I'd now like to welcome our third speaker, Carmine De Ora. Since 1987, Carmine has been working for Webuild in the field of construction of large railway and road infrastructure, and has gained considerable experience in the construction of very long and complex tunnels. Among the projects in which he has worked, we can mention the Bologna-Florence high-speed rail section, the Salerno-Reggio Calabria motorway, 5th and 6th, Macalotto, the reconstruction of the Polsevera viaduct, Genoa and the Milan-Genoa high-speed capacity line called the Terzo Valico dei Giovi, Genova Junction 1 project. Please welcome Carmine De Ora.
Good morning, I'm Carmine Dauria, and today I'm going to talk about some safety solutions applied on the Terzo Valico dei Giovi project that you have already heard from my colleagues Leonardo and Remo. Worker safety is the main goal in our project. We put our effort in giving workers positive examples to imitate and in raising awareness of the many responsibilities that everyone has in the field. To achieve the goal, we organize special training courses, theoretical and practical. One of the main actions was to spread our safety culture among our subcontractors who participate in the project. We have changed the classic approach based on vigilance and punishment, and we have decided to listen to workers and share with them the possible safety solution to improve their working conditions. As a consequence, we have introduced the training on the job project to empower the workers' skill directly on their workplaces. The Webuild Safely program has allowed the project to keep going during the period of the COVID-19 pandemic. The program was based on the self-search for positive cases of the virus, using antigenic and molecular swabs. Moreover, the project provided for dedicated accommodation to guarantee isolation in the base camps and advertised a vaccine campaign directly in the infirmaries. The Webuild Safely program has allowed the entire project to keep infection under control among employees and subcontractors and to break the chains of contagion. Let's move on to another great challenge faced on our sites: excavation with traditional methods in rocks containing asbestos in a mineral matrix. In fact, during the excavation of Cravasco Edit, a very complex geological formation was encountered at kilometer 0.660. In this case, the consortium adopted an innovative organization of the tunnel excavation aimed at preserving the health of the workers and the external environment. The geological formation contained asbestos mineral composed basically of chrysotile and a minimal part of tremolite, and the challenge was not to spread out the dust produced during mechanical hammer demolition. As everyone knows, exposure to asbestos fibers can cause serious risk of mesothelioma and lung cancer. The risk of developing this disease depends on the concentration of asbestos fibers in the air and the time of exposure. In fact, through breathing, these microscopic asbestos fibers are introduced into the lungs and alveoli, with the possibility of developing these terrible pathologies. Unfortunately, the spreading of asbestos fibers in the air is not just linked to the rock abatement, but also to the subsequent lifting of dust due to the drying of the mud or to the fibers contained in the water used for the abatement. In this slide, it's easy to see how a particular equipment of the entire tunnel allows to contain the dust raised in a small area close to excavation phase. One of the main solutions was to adopt an extraction ventilation system together with an HEPA filter capable of purifying the air up to 99.96%. The extraction ventilation system makes it possible to invert the airflow introduced into the tunnel, creating an airflow that enters from the tunnel entrance, runs through the entire tunnel, reaches the excavation phase, and is sucked by the rigid pipe in the excavation phase. Through the rigid pipe, air reaches the HEPA filters and finally is released, purified, into the atmosphere outside the tunnel. The heart of this system is therefore represented by the extraction ventilation system. It consists of two fans of 200 kW each and a complex set of filters which together guarantee the extraction of about 60 cubic meters per second of air. The filter system is self-regenerating and is capable of carrying out backwashing. The tunnel has been divided into three distinct areas, A, B, and C, separated by physical barriers equipped with sliding guillotine doors. According to our experience, A zone, contaminated area, must be as short as possible and between 60 and 80 meters from the excavation phase, while B zone, the contamination area, can be about 1 meter long. Instead, the C zone, not contaminated area, is represented by the rest of the tunnel and the external yard of the construction site. The number of people present in A zone is limited to 3, with rotation every 4 hours in order to withstand the severe condition imposed by personal protective equipment. In B zone, it is only possible to carry out the contamination operations of workers and vehicles. Here, we can see the physical barriers equipped with sliding guillotine doors. The water purification plant, set on the external yard, guaranteed through ultrafiltration the removal of asbestos fibers contained in the water. The filtration and purification of water was one of the key elements for the success of the operation. In fact, all the water coming from the tunnel and purified through the ultrafiltration mechanism could be reused for the abatement of dust during excavation. The excavated material was treated as waste containing asbestos if it had a concentration 1000 mg per kilo, and as a byproduct if it had less than 1000. In the first case, the automatic bagging was carried out inside a structure mounted in the external yard. In this structure, the rock was further crushed and loaded into bags with a volume of 1 cubic meter, which were loaded on trucks to be transported to authorized landfills. Personal protective equipment were electro-respirators equipped with an absolute HEPA filter connected to a full face mask that makes breathing easy. safety boots, gloves, high visibility braces, Tyvek overall, which had to be thrown away at every exit from the tunnel to prevent the spread of asbestos fibers to other places. In this slide, we can see the concentration of asbestos fibers that occurred during the most critical days, and we can see that normally asbestos remain below 50 fibers per liter, while one day there was a peak of 190 fibers per liter, but always with maximum worker protection and no fiber spread in the external environment. As we can see from the graph, in A zone with the histograms in red, we find quite high concentration of fibers, while in B zone, that is the contamination area, we find low values. While in C zone, we find values close to zero, or in any case, lower than 1 fiber per liter. Here we can see the monitoring points that allowed us to keep under control every day, during each excavation, the concentration of asbestos fibers in each work area. We invest in the developing of safety. Other safety actions that have been undertaken to improve safety are the semi-automatic steel ribs that allowed to carry on activities on excavation phase in absence of people. In fact, it is known that the most serious accidents due to small release or collapses of rocky portions can occur in this point of the tunnel. Therefore, the operations that previously took place as represented in these pictures with the semi-automatic steel ribs can be performed in absence of people directly exposed on the rock collapses. The same thing can be said for steel inverts, which can be mounted with a special device attached to an excavator. The organization of the emergency is another highlight of Terzo Valico dei Giovi project. The challenge of emergency operations was to face a 53 km construction site, mostly in tunnels, with hostile and difficult environment, like methane and asbestos. For this reason, was created a rescue system called CIS, consisting of an operation center that collects emergency calls with 6 infirmaries equipped each with an off-road rescue car, capable of reaching all the working places within 20 minutes from the emergency call. Thanks for your attention.